Someone requested for a possible solution for this problem. So this will be my possible solution. So the question reads: a motor to be used in an engineering machine component is hoisted on a horizontal platform. The combined weight of the platform and the motor is 17,500 Newton. Take D to be 1.2. The point C is moved to and located on the positive y-axis. Determine the tension in each cable for equilibrium. So this is an equilibrium equation, so we know that all our forces will equate to 0. So if we sum all our forces, so here I've written all the vectors that are on the sketch. We have TA, so we can call this our TA. We can name this one vector TP, and this one TC, this one TD, and this one going up TA. So if we add vector TB, C and D, they will equate to the magnitude of vector TB plus TC plus TD. It will have the same magnitude as TA. But if you find the resultant of vector TB plus TC plus TD, that vector will be in the opposite direction as TA. So first thing that we're gonna need is our coordinates. So we've identified our force vectors. So this is how I'm gonna represent the force vectors. So for TA, we only have the Z component going upwards. So it's 0I plus 0Y for the Y component plus 17,500 Newton for the K component. We know the K component. This is due to the weight of the combined weight. So all the force vectors are in Newton. Then for our following vector B, so to get vector B, we need some scalar that we can multiply the position vector AB with. So I'm gonna be solving for the scalar. So there is another method where you use the unit vector, but I won't use the unit vector method in this case. Here, vector C, I need some scalar C multiplied by position vector AC. And for vector B here, some scalar C, some scalar D multiplied by position vector AD. So now we need our position vector. We need our position vector, so we need the coordinate to help us find the position vector. I'm gonna erase this. We're writing down our coordinates, so we need our coordinates. Coordinate B, well, let's start with A. We have 0, 0 and 3. The elevation is 3. And coordinate B, we have 1.2 as our x coordinate, and minus 0.9 for our y coordinate. And for the z coordinate going upwards, it's 0, it's on the xy plane. For C, it was mentioned that d is 1.2, so this distance is 1.2. Going back by a distance of d, which is 1.2, we go back to the y-axis. So the coordinate for C is 0, for the 0.9, and 0 for the z. Then for D, we are only given the distance from the edge going in this direction, so we are given that this distance is 0.6. so we know that the half of the width, the width of the plate divided by 2 is 0.9. So we know this is 0.9. Then to find, let me draw the x coordinate, the x-axis going in the negative direction. So this is the coordinate that we need the y coordinate for point D. So to get it, we have to use this 0.9 and 0.6 distance. So it's 0.9 minus 0.6, then we get 0.3 meters. So that's 0.3 meters. So writing down the coordinates of D, we have minus we have minus 1.2 for the x this distance, and for the y coordinate, which we've just discussed, is 0.3. And I believe this is where most people were going wrong. They used the 0.6. Then for the z coordinate, it's 0. So we have our coordinates now, so we can create our position vector and come back to our equation, and substitute into our equation. So position vectors. Position vector AB. So it would be the coordinates of B minus coordinates of A in this case, and we will get 1.2 I minus 0.9 J minus 3 K. So this is our position vector. Then for position vector AC, coordinates of C minus coordinates of A, those would be the component of our position vector. This is what you should get, minus 3. Okay, position vector AD, B minus 1.2, same process, minus 0.3 J minus 3K. So we have our position vector, so we can now, so these are our scalars. So for me, so these are the scalars that I need to find that would give me the vectors that I need. So here the scalar, I can take it just as 1. So our force vectors, for TA, we already know TA, it's 0. You can just write the scalar 1 if you like. 0I plus 0J plus 1 K. For TP, we have our scalar b, a position vector that we got above, minus 0.9 j plus minus, sorry, then cc, it's 0 I plus 0.9 j, so be careful of the signs. Then t d, the last one, it's minus 1.2 I plus 0.3 j minus 3 k. So now we just have to apply this formula. You can call it equation 1. So since we have a vector, we're gonna add all the x component. So the x component here for TA is 0. For b, it's b. So you can multiply with the b. This you can multiply all the components with the scalar. So my x component here will be 1.2b, yeah, 0c, yeah, minus 1.2d. So I'll add all the exponent together. So I'm adding the x component here. For the b, for vector b, it's gonna be 1.2b plus 0c minus 1.2d. So now moving to the y component, so they will equate to this x component will equate to the TA x component. Remember we're using this equilibrium equation. So we'll have 0 in this case. It's equal to 0. This x component is 0 for TA. So I mean the y component, we will get where the other video stopped. So never mind what's on the right hand side of this line. So this is where the last video stopped. So I was summing all the x component. So here I was summing all the x component. They're gonna so all these x component for vector b, c, and d, they will equal to the x component of vector a. We are referring to this equation 1, or equilibrium equation. So we did the same for the y component, summed all the y component and equate them to the y component of vector TA. Again, perform the same calculation for the z component, equated to the z component of vector TA. So after that, you'll have 3 linear equations with 3 unknowns. So you can use any method of your choice to solve for the unknowns. You can use the methods that you've learned in linear algebra, or you can just use the simultaneous equations. So I did not show the calculation process where I was finding my unknowns, which are my scalars, multiplying my position vectors, which will then give me my vectors, my force vectors. So these were the scalars that I found. So now the question wants us to find the magnitude of these vectors b, c, and d. So we are not done yet. So we'll go back to our equation. For example, we'll go back to this force vector b. So we're gonna substitute our scalar, which we got to be minus 2187.5. So substitute it, and you can then find your vector TP. So once you've found your vector TP, you can then proceed to finding the magnitude, which is 736.89. So it's going to be the similar process for finding the magnitude of TC, force vector TC. So the scalar for TC was minus 1458.33. That was our scalar C, multiplying the position vector AC. So again, substitute your scalar, then you obtain your force vector TC, find the magnitude. So it's going to be the same process when obtaining vector TD. I did not do the calculation for TD, but as you can see, the values are close to the answers given in this problem. This is due to the rounding off, but they are close enough if you pay attention. So this is how you attempt these kinds of equilibrium questions.